Alright, calculus, sorry for not getting this video up earlier to you guys, but we're looking at number 33, the area between curves. I'm going to jump right into kind of an explanation of the basics. It has to do with negative space, and if you guys remember what negative space is, the general idea for that is you take the whole of something, you subtract part of it, and you get leftover. So how does this apply to area? Here's what we would get. Let's say that we took, a whole area like this, and let's say there's our curve, just some fancy curve. Now I'm going to kind of take this piece and duplicate it a few times. Oh, don't really want to do that. Let's take a picture of it. There we go. Put it on this page. Okay, so here we have this same area. And if we wanted to take, just the inside of a couple of lines. So let's say I have another line underneath this, and it's, I don't know, something like this. So then we got that line. And if we're looking for the space between it, these blue lines that I'm talking about here, how could I figure that out? Well, the idea is that we have this space underneath it, and that's the part that we're going to subtract away from the whole purple thing. So, we got this red space, and let's go ahead and here, let's do this just to make it a little bit cleaner. You guys will see why I'm doing this here in a second. It's not a big deal, but we're going to take a photo of this bottom piece and then duplicate that. So here we go, take a photo, but just this piece. Try to get that blue out of there. So current page. There we go. Shrink it down. It needs to be shrunk down quite a bit more. Quite a bit more. There we go. That looks a little bit better. Okay, so now we're looking at that curve, and if we subtract that, then we'll be left over with the blue. So I'm going to fill this blue back in here. Now if we're just trying to find the blue area, not all of it, just the blue. And so I'm going to do the same thing here. And if I want to take that area, all I got to do is take this red and subtract it out. And if that's gone, then I'm left with the blue. So I take the whole thing, the blue and the red together, which you could say is kind of like the purple. And then I'm going to subtract out that red, and then all we have left over is the blue. See? Take it away, and you get the blue part. And that's what we want. We want this line here that's left over. Now the details that matter in that, well, we got, just the general idea of finding the area of under a curve. We need to know our start point. We need to know our finish point. Now in order for us to figure this out, taking the whole area, which would be like the purple line right here, our top line, and then our bottom line. So here's our bottom down here, bottom. We got to know what's the bottom and what's the top. And similar to just fundamental theorem of calculus where you got the B and the A, we're going to have this consistent theme of top minus bottom. Okay, so let's see how this plays out. Now here's a big complex definition of how it relates to the sum as it goes to infinity and all those things. But let's just jump right into the numerical examples. Okay, so here's an idea that we also need to watch. So we said it's top, this is our top piece, and then bottom, in this case would be g, so we're doing f of x minus g of x, but notice the difference between these. Right here we're both positive, we got positive top, positive bottom, and then we have a positive top and a negative bottom, and then a negative top and a negative bottom. So let's see what these lines are at about. Well, this first one, it looks like it's at about 7. I don't know, not really, I don't really know what it's at, but I'm just giving a number there. And if that were 7, then this would probably be about 3. Well, then this next one looks like it's at about 3, kind of at the top, the bottom where the other one was, and then this down here would be 4 below that, which would be -1. And then for these bottom two lines, this top one would be, or these two negative lines, not two bottom lines. Let's say that's -1, then this would go down to -5. And I just want to show you guys how numerically this kind of balances out. So let's just pick like one line like it does here and see how the calculations work out. So if we're doing a top number minus a bottom number, that's kind of like 7 minus 3. And then when we go here across the axis, we would have 3 minus -1. And then for the third one, we'd have -1 minus -5. Now, no matter how you place it, whether it's high, medium, or low, across, both below or both above, you still come up with the same number, 4, in each case. Which means, really, that it doesn't matter. Our intuition would want to tell us that there's a difference of positive and negative numbers, but not when you're making this calculation. When you want to calculate the distance between two pieces, you just have the end minus the beginning, or the whole minus the part. That negative space calculation. So let's just do it. Let's make it this easy. Okay, so whenever we're looking at the area between two curves, we got to have all four sides enclosing it in one way or another, which means we need to know what the top equals, we need to know what the bottom equals, we need to know what the left side, or the start, you could say. We need to know what that equals, and we need to know what the right boundary is, or the finish. We need to know all these. So the top one in this case is red, and the bottom one is green. I'm going to go for some consistency here, and I'm going to go ahead and color this in blue. And I'm going to do the bottom one red, just because I want to be consistent all the way through. So I'm gonna pick those two colors and stick with them. So the bottom one was red, the top one was blue. So let's color code our things. Now I don't know if you guys have it here in your thing, but I think you do. But this is our sketch of the curve. One thing to keep in mind is that our boundaries don't fill the entire screen. Notice here that the start and the finish is just from 0 to 1. So we're talking from here at x equals 0 to here at x equals 1. So we just want this space in between. Okay, so to find that space, we need to figure out what the top piece is. Well, the top out of these two, how could I figure it out? Well, there's a couple ways. I see that one is a quadratic, which means nonlinear or curved, and the other one's linear. So I'm going to start with the linear one, actually. That's a little bit easier to define. And that's this one. So this is y equals -x. And then the top one is the quadratic, which would be x squared plus x plus 2. So that's our x squared plus x plus 2. And that's it. Now, here's the interesting thing. I don't know if you read this detail, but we're not going to go through fundamental thermocalculus, which means the whole power rule, take the antiderivative, plug it in, and see what you get. Most of these type of questions on an AP test are really just asking that you either set it up or use a calculator. You don't actually have to find the calculation. Now we can, and we can do it by hand. I can show you that, but really we're just looking for the setup and the calculation by calculator. So let's get that worked out. One thing just to note here, I know I put these here, but I never filled them in. This was x squared plus x plus 2. For the top, it was -x. For the bottom, the left side was 0, and the right side was 1. Okay, so the integral then is from 0 to 1, and we're going to have the top piece minus the bottom piece. And the top in this case is x squared plus x plus 2. The bottom is -x. Do notice this, that if we were to work out the simplifying in algebra, we got minus minus. So got to watch those negatives and positives. That's going to make a big difference here. All right, next it says the area is. Well, we're going to calculate that. So I need my trusty calculator here. I'm going to go through and restart some of this stuff from scratch. What I'm going to do is enter in my actual top and bottom pieces, and then I'm just going to subtract them. Okay, so let's do the top. The top is x squared plus x plus 2, and then the bottom is, what was it, negative x. Okay, now to find the difference between those two, it's really just, one minus the other. So we can take our y1 minus y2. Let's do that. We go to variables, y variables in this case, and we're doing function, and then y1 minus, now we're going to do the same thing, variables, y variables, function, and y2. Okay, so I have y1 minus y2. So now I would have three functions being graphed there that I would take the integral of. But instead, I'm going to turn off the first two. I'm just going to find the difference, the top minus bottom. Now when I go to my graph, this is what I get. Let's take my window and make it a little bit different. Let's start at 0, but we're going to do the same window that we have on the screen, 0 to 2. And this is going all the way up to 20. I'm just going to go up to 10. Let's see what we get. Alright, that looks a little better. Now, do notice that it doesn't quite look like the other one because it's all positive. We're just doing the top minus the bottom. And you're going to get a positive area when you're just taking the area between two curves. It's a little bit different than having area below the x-axis being negative and area above the x-axis being positive. Because in reality, when you subtract that bottom area, it balances out like we saw a second ago. If that just confused you, don't worry. We're calculating the area of this top minus bottom curve from 0 to 1. So I'm going to do second, calculate area, which in this case is 7. Left in 0 and right is 1. So 3 1/3. All right, that was easy. 3 1/3. The area equals 3 1/3. If you were to do that in proper fraction, you'd have 10/3 or 3.3 with a bar, however you want to say it. All right, next. So right away, we're going to jump into how does this actually get complex? So notice a couple things here. We have our top curve. I'm going to shade it blue again. So we have this top curve. Oops. Going off the line there. Okay, so we have the top curve and the bottom. We know this is top. We know the other one's bottom. We have the same relationship where the bottom one was linear and the top one was quadratic. So this is 6 minus x squared. And the bottom one is negative x. But we're going to run into something that's a kind of a snafu here, something that's a problem. Because when we say the integral, and we got the top minus bottom, so that part's pretty easy. So the bottom's negative x, and the top is 6 minus x squared. And of course, remember that these should have a dx on them. I didn't really put them on there. But these are all multiplied by dx because we've got to be doing it with respect to x because we're moving in the x direction. All right. So we got that top, we got the bottom, but we're missing left and right. We're missing this point and this point. So we got some issues. And the issue is, how do we figure out what that left and right is? Now, it looks like this is at about 3. Not sure. And it looks like this is at about 2. Again, not sure. So how could we actually figure that out? Well, something interesting is happening here. This is an intersection. And for an intersection, we know that the top and the bottom are the same. So if we figure out when those two functions are equal, then we can figure out where that x value is. And maybe it's at 3 and 2, but we don't know. Let's check. I'm going to do this by hand, but then also show you how to do it with a calculator. Because honestly, this is more of a calculator type problem, but this part might be asked of you to do by hand. So if we're doing the top equals the bottom, that would be 6 minus x squared equals negative x. Now, that's our top and our bottom. They're equal to each other. I notice that I have an x squared in here, which means I should treat this like a quadratic function overall. And that means I'm probably going to get all the terms on one side equal to 0 and do some factoring. I know it's also easier to factor if x squared is positive, so I'm going to move this x squared over to the other side. I'm going to move the 6 then as well. And that would give me x squared minus x minus 6 is equal to 0. Now that's pretty easy to factor. What multiplies to negative 6 adds up to negative 1. Well, that means I got a plus and a minus. It's going to be a minus 3 and a plus 2. So what do my x values equal? Oh, I just made a huge mistake. Notice this. This is not negative x. That's positive x, which means that's positive x, which means this is positive x. How did I know that was an issue? Well, because my x values were about to be off. So that means here, that plus should really be a minus, and that minus should really be a plus. So take this back. There we go. Okay, so we got x minus 2 and x plus 3 equals 0. And that tells me that x does in fact equal 2 and x does in fact equal negative 3. Okay, so there's my start and finish. That's when the two graphs are intersecting. So I would have from negative 3 to 2 of 6 minus x squared minus x. I almost did the negative x again. And then we got a dx. All right, so that's it. Oh, wait. I just rewrote the integral. I didn't need to do that. I really just needed to add in the area calculations to the other piece. So I just need to calculate this now with my calculator. Now, because I've already set up the third equation here as top minus bottom, I really just need to fix the top piece and the bottom piece. I need to fill those back in. So the top piece was 6 minus x squared. I can delete the rest of this. And the other piece is not negative x, but positive x. I do need to change my window, because the window does have to include everything. So let's make it match the window we see on our picture. From negative 4 to 4 works pretty well. And then it looks like from negative 5 to about 5 for the y direction. So we'll say negative 5 to about 5. There we go. All right, so let's graph. Actually, let's go here. And just to make sure that this is right, oh, I told you I was going to show you how to solve for the intersection. So we got that, that, and there's our third curve, which is the difference between the two. Well, I'm going to turn off that third curve, because if I'm solving for the intersection, I really just want the first two curves. So we go to our graph, and that does look just like what we have. So I'm going to do second and calculate for this intersection. If I click on 5, that'll give me the intersection. The first curve, where are we at? I don't even see where we are. Oh, we're way off the screen, that's why. Okay, so we're coming back, we're coming back, we're coming back. Pretty low here. Right, that looks pretty close. And that looks close enough. And guess. And it says at negative 3. Actually at negative 3, negative 3. That's, coincidental there. Now if we want to do another calculation for the intersection, we do the same thing, but this time we go all the way over to the other side, which we know is going to be at 2, but I'm just trying to confirm it with my calculator here. And we get all the way close to 2. Close enough. And then just click 3 times for both of the pieces. And then at 2, 2, hey, that was coincidental as well. And that's actually just because the second function is itself y equals x. Anyways, details aside, it works. Now we just need to calculate the area between those. So now I got to turn these first two functions off and calculate the area of the third one, which is the difference between the top and bottom, the top minus the bottom. Okay, so now we go to our graph, and we're going to calculate the area from negative 3 to 2. So second, calculate area, number 7, left is negative 3, right is 2, and the area is 20.8333333333. So what would that be in fractions? That's kind of interesting. How do I make that into a fraction? Well, there's a few different ways, but honestly, not a big deal. 20.83 with a bar. Check done. All right. Next, let's keep going with this. Find the region bounded by the graphs x equals 0 and the first intersection of sine y and y equals sine of x and y equals cosine of x. Okay, so the first intersection, where does that mean? That's x equals 0 is the left. So we got this is the left side. Here's our left boundary. But then right here is that first intersection, is the right. So when does this happen? And that's not exactly easy to do. So first we got to figure out when is that intersection between them. We can do it algebraically, which in this case it's asking us to do. We can also do it with a calculator. So the idea is to figure out when does sine of x equal cosine of x. Well, there's a couple of ways that you can work this out. The most straightforward, I guess you could say, without trying to do a lot of problem solving, if I divide both sides by cosine of x, then I get sine of x over cosine of x equals 1. And then the question is, how do I simplify that? Well, sine over cosine, that's the same thing as saying tangent of x equals 1. And if tangent of x equals 1, then we can just take the arctangent of each side. Well, I'm going to throw in some problem solving to try and keep it simple here. We know that tangent of something equals 1. And what would that be? Well, it'd be 45 degrees or pi over 4. So that must mean that x equals pi over 4, which is about 3/4, about 0.75, which makes sense. That's about 3/4, about 0.75 there. It's actually just slightly bigger, which is what you should expect. So this is pi over 4. So we figured that out. Now we just got to set up the integral. We got to figure out which one's on top, which one's on bottom. So here comes some knowledge from your trig graphs and values. We know that sine of x is in fact 0. So in other words, sine of 0 equals 0 is what I was trying to say. So that means it's the bottom one here because it starts at 0. Cosine of x, on the other hand, is this one up here. So that's our top. So when we set up the integral, we're going to have the integral from 0 to pi over 4, which we figured out, of cosine of x minus sine of x. Because remember, it's top minus bottom. And of course, we do need that dx in there just for proper grammar and the idea of our direction of movement. So what's the area? Now we go to our calculator. So calculator, y equals, top one was cosine of x, so I'm going to do cosine of x and delete this extra piece. And the bottom one is sine of x, sine of x. And again, we don't really need the top and bottom. We could if we wanted to, just to get it to look like the other picture. But we know what our start and our finish are. It's from 0 to pi over 4. So now when I go to my graph, well, it looks like that's going to be a pretty straightforward area. Looks like it's just going to be 1. So y, or that's not what we want. We want the graph. And sine, or second calculate, there we go. Area, sorry, I got too many things going on in my head. Left side 0, right side pi over 4, so second pi divided by 4. And it says 0.7799. So we're looking at approximately 0.7799. Now that probably actually has some, very easy calculation. So I want to go ahead and do this one by hand. We know the antiderivative of cosine is sine, and the antiderivative of negative sine is positive cosine. So that's pretty easy to do. We're evaluating that from 0 to pi over 4. So if we were to do f of b, the top minus the bottom, again, same kind of theme. Sine of pi over 4 plus sine of 0 minus cosine pi over 4 minus cosine 0. Okay, so sine pi over 4, that's square root 2 over 2, square root 2 over 2, or 1 over square root of 2, plus 0, minus cosine is square root 2 over 2, minus, then we got minus minus, so that's plus 1. Now I'm seeing that this actually equals 1, so this right here is a puzzle. Maybe the calculation is slightly off. So I need to go back and just double check this. We're going from 0 to pi over 4, and it says 0.7799. Let's take a look at our pieces. We got cosine of x, sine of x, y1 minus y2. Second, calculate. We want the area. We're going to start at 0 and work our way to pi over 4. Which would be second pi divided by 4. Do we get the same thing? We are. So I'm missing something here, probably in my calculation. You guys probably already see it, but I'm not sure what exactly I'm missing, because from this graph, honestly, I would think it is about 0.7799. Algebraically, I'm probably doing something wrong. We got sine of x. Oh, that's why. I see. You guys are like, Mr. Butler, you're just being stupid now. So this is exactly what's going to happen. Sine of pi over 4 plus cosine pi over 4. Can't even plug things in right here. Minus sine of 0 minus cosine of 0. So what that does then is it winds up kind of doubling up some of these things here. And this is a plus. So that's going to have a minus 1. Then we got plus square root 2 over 2. So this all together equals square root of 2 minus 1. Now that actually does sound like it would equal 0.7799. Okay, so good. The numbers balance. We feel good about it. At least I feel better. All right. What? This is crazy. What's going on here? Why is this that much harder? It might not seem that much harder, but remember the four things that we got to be checking here is what's the top, what's the bottom, what's the left, and what's the right. Because something really different happens with this one. If we notice that we have a red curve here, so the red curve is on top here, but then on bottom here, and it matters that it switches because that's two different types of integrals. And then similarly, the blue is bottom to start, but then top to finish. So we have two separate integrals. The one for this left side before 0 is going to be the integral from something to 0 of the red curve minus the blue curve. And then the other one's going to be an integral from 0 to something of the blue curve minus the red curve. So let's figure out what the blue and the red are. Well, I see one's a cubic, one's a quadratic. And cubic is the only one that would have this max and min relative extrema in there, where it's got two bends in the curve. So that tells me that the red line is cubic and the blue line is our quadratic or squared and to the power of 3. So the first one, let's call this f, and the second one we'll call g. So then we're going to have f minus g, because the f is on top the first time. And then the second time we're going to have g minus f. Okay, so we got two integrals, and then if we add them together, we get a sum total, and that would give us our actual answer. Now, there is a shortcut to doing this. I'll talk to you about it in a second here. But let's see what we can do to set these two problems up. Well, we got to find those intersections. We got to find this one way over here and this one way over here. And they both look like they're at 3, but I don't know that for sure. I have to confirm it. So let's do the algebra. That means I got f equals g. I got to figure out when f equals g, when our two curves equal each other. Well, the f1 is 2x cubed minus x squared minus 14x. And the other one is 4x minus x squared. Well, some easy algebra. We can get rid of the x squareds right away by just adding x squared to both sides. And then we have 2x cubed minus 14x equals 4. Oh wait, that's 4x. That's even easier. You will see why here in just a second. A couple things I can do. Let's go ahead and combine this 4x with the other x on the other side. That would give me 2x cubed minus 18x equals 0. At this point, I could divide both by 2 or even factor out a 2x. I'd be left with x squared minus 9. So now I'm going to have 3 factors because this is a difference of squares. The square root of 9 is 3, so that's going to be 3 and 3 plus 3 and minus 3. Square root of x squared is x, and we got the 2x. So that means that x equals 0, x equals negative 3, and x equals positive 3, which confirms my original suspicion that they crossed at 0, but now I can be totally sure of that. And right here we know that this is at 3, and this down here is at negative 3, for sure. So to kind of complete this setup, we're going to go from negative 3 to 0, and then from 0 to 3. So the integral would be, formally here, negative 3 to 0 of the top minus bottom is going to be, what was it, 2x cubed minus x squared minus 14x. Then we got minus the bottom, which in this case is 4x minus x squared. Plus, we got a second integral here from 0 to 3 of 4x minus x squared, that's our top the second time, minus 2x cubed minus x squared minus 14x. dx, of course, on both of these, just for good grammar. Squeeze it in there. So how do we calculate that area? Well, we got a couple of things to do in our calculator. I'm going to go back to my y equals. So we have this 2x cubed, 2x to the third power, minus 14x. Is there something else in there? Oh, we got a minus x squared as well. Let's throw that in first. It wouldn't make a difference where we put it, but just so you guys don't get confused. And then we got 4x minus x squared. Now the first one that we want to do is the cubed minus the squared, the cubic minus the quadratic function. So we're going to do y1 minus y2. Let's go ahead and graph that. And this one we're just going to do from, oh, we should turn off the first two so we don't get really confused here. So let's do y equals. We're going to turn off these two first graphs because we don't really need them. We'll go to our graph, and you know what? Let's take a look at how high does that graph go. It goes all the way up to 20. Okay, so for our window, let's change this window from -20 to 20, and we'll count by 2's. Okay, so there's our graph, and that even goes nearly off the screen as well. So here's our first half, and notice it's the top minus bottom, but when they switch, and this is kind of interesting, this is very interesting. All that it does is it takes that area, but it's going to make it negative here. So that's why we're going to do the opposite, y2 minus y1, which makes the negative into a positive, and then we got two positive areas, and then we add them together. Well, let's go ahead and calculate that. Let's see what happens. So I'm going to do second, calculate the area, number 7, and this first one's from -3 to 0. And we get 40.5. Now I have a suspicion that the other one is actually going to be equal. So let's see what happens with that. Then we'll show you some shortcuts. So for the second one, now I'm going to go to the y equals. I'm going to do a new curve here. I'm going to switch those around. So variables, y variables, function, and this time I'm going to do y2 minus y1. So now I'm going to turn this first one off, and you guys will see what happens to that area this time. Now it's going to go negative and then positive. We want this positive side over here. So let's graph that. Or not graph that, let's calculate that. Second, calculate 7. And now we're going from 0 to 3. And we get 40.5 again. So, surprise, surprise. But here's what's, most interesting to me. Is there a way that I could have done all that instead of having to do it two separate calculations? And guess what? There is. With your calculator, there's an interesting thing we can do. It's kind of a shortcut. So I'm going to insert a page here so you guys can see what we're about to do. So we're going to take those two graphs and kind of put them into one graph, because if I were to graph both of these, we would get this piece, but we want the top one of the first one and the top one of the second one. So how do I make these negative pieces go up to the bottom? Well, instead of saying, y2 minus y1 or y1 minus y2, how do we make negative areas turn into positive? How do you make a negative value turn positive? I hope now that in your head you're thinking, wait a second, can't I just do absolute value? Yes, you can. So where's that at? Math, num, absolute value. And I'm just going to do absolute value of my y3, the third function that we have going on there. Function y3, close that off. Okay, so now I'm going to turn off this third function, and I'm going to show you guys what happens when we take the absolute value. Look, we got a positive area, a positive area. Ooh, isn't that awesome? Both areas positive because I took the absolute value of those areas. So then I can just calculate calculate, go all the way from -3 to 3, and I should get 81. Yeah, check that out. Okay, so let's put this on the screen here. Let's put the other ones on the screen as well. So here we go. So now we're going to do, let's see, let's turn this one off, but let's turn this one back on. Yeah, that's what we want. Graph. There we go. So now I'm going to take this, put it over the top of that one. Excellent. And you know what? I'm actually going to take the area. Let's redo that. Second, calculate 7. We're going to do the area. And whoops, it already went to the second thing. So second, calculate area, lower limit, -3 to 3. So we got positive, negative, and the area, it actually equals 0, but this thing is trying to say, is it really 0? But it has like this point 0.000000003 and so on. So we got this area that is, pretty much just 0. So let's see what's really going on here. We can delete this middle one. Delete, delete, delete. Okay, so here's what happens. When we got this positive and negative area, but we want to flip the second piece up to the top by taking the absolute value, now we get two positive areas instead of one positive and one negative. When we take the absolute value, it flips it up. That is the advantage of using a calculator. It is awesome. All right, let's keep going here. All right, find the region bounded by the graphs 12 minus x squared, y equals negative x, and y equals 4x. So here's what's really happening with this one. And when I look at this, there's kind of a question mark. Does it mean this piece here, this piece here, this piece here? Let's just do it all. So this has some interesting combinations. We're going to start with the red being our first top all the way here, minus the blue being our first bottom. So that's going to be our first calculation. We're going to do the first top minus the first bottom, so T1 minus B1, and we're going to go from A to B. So let's call this point right here, it looks like it's at about -6, but that's going to be our A, and B is going to be the split right here in the middle. And you guys are going to see why we're looking at that. So we're going to do the first top minus the bottom from little a to little b, and then we're going to add on that a second calculation. And this time the red one is still on top, notice that, but now it's the green that's on bottom here. So when we put the red and green there, now we're going to have the top one, or the top again, but minus the second bottom, B2, you could say. So here's our B2, and here's our B1, and here's our top the whole time. Top, top. It's top first and second. Okay, and then that would enclose this whole area. And it's got a switch there in the middle. So essentially, we're kind of ignoring this green. It's like it doesn't exist until we need it for the second half. And we're ignoring this blue in the second half because we don't need it. We just want the green. And then that will give us that kind of hooky shape there. I don't know what you would call that. Looks like a boomerang or something. So let's figure out, for the second piece, we said this was B. Let's go all the way to C, B to C, a new left and right for that second integral. And that'll give us this space in between. Okay, so now that we're looking at these pieces, shade the region you're trying to find. Well, we did this kind of backwards. The integral is, okay, so we're going to have two pieces. And, we're going to have the top minus the bottom. So let's figure out what these pieces are. Okay, so we got two linear functions and one quadratic. That means that the red one is quadratic. And then the blue is linear, but it's positive, so it's going to be the second one. And the green is linear, but it's negative slope, so it's going to be the middle one there. So B2, we could say, is negative x, and B1 is 4x. And then the red here, this quadratic, is 12 minus x squared. All right, so let's use our calculator. Let's set this up. That means we're probably going to be using our first three calculations. So the first one is, 12 minus x squared. So we got 12 minus x squared. Don't need the rest. Now I already got a 4x in here, so I'm going to have that be my blue, which I actually kind of wanted. And we need the red minus the blue to start, but then we need the red minus the green to finish. So that's going to be vars, y1, but this time, oh wait, let's kind of switch some things around here. We need a third function, negative x. So for the first one, the first half, we're going to do y1 minus y2, the red minus the blue, you could say. Whoops, that's not what I want. There we go. Y vars function y2. And then for the next one, it's still y1. So we're going to do vars, y vars. It's the red, which is y1. But this time minus the green, which was y3. Alright, so we got a whole bunch of stuff going on. Now I'm going to turn off these original pieces because I really just need the areas to calculate. So I'm going to go to my graph. And there we go. We got two curves. So I need to do these one at a time. Let's start with the y1 minus y2, the red minus the blue. We're going to integrate that one. Oh wait, we don't know when those are equal to each other. So we got to calculate that. We got to figure that out. When does the red equal the blue? When does the red, the top one, equal the bottom one for this first piece here? Well, that's 12 minus x squared equals 4x. Now again, we got quadratic. It's easier to factor quadratics if the x squared term is positive. So I'm going to move these two terms over. That would give me x squared plus 4x plus 12. Is that right? No, minus 12. Equals 0. Now if I were to factor that, I would have x plus 6 and x minus 2. Which is true, because look, right here there's another intersection at x equals 2, but that doesn't really matter. The one that does matter is negative 6. So in fact, a equals negative 6. Now, this middle piece, b happens when negative x equals 4x, and it's not too hard to figure out that that only makes sense if x equals 0. You don't want to divide by x on both sides, because then you get negative 1 equals 4, and that's not true. So that must mean that x can only equal 0 in that instance. So let's figure out what c would be. Well, that's when the top second time, which is still the red, minus the bottom second are equal to each other. So we'd have 12 minus x squared equals the green, which is negative x. Now similarly, we're going to move these quadratic terms to the other side to make the factoring a little bit easier. X squared minus x minus 12 equals 0. Now factoring these pieces, we'd have two x's, and one's going to be positive, one's going to be negative. We have a plus 3 and a minus 4, which again makes sense because right here we have x equals negative 3, but that's not needed. We don't need that. That's not necessary. We need the positive side, which is at x equals 4. So b, or not b, pardon me, as we sing, c equals 4. Okay, so c equals 4, a equals 6, and in the middle we got b equals 0. So now we got our boundaries, we got our tops, our bottoms. Let's set it up. Negative 6 to 0 of the top, which is 12 minus x squared, and the bottom in this case is 4x. I don't need parentheses because there's not really a mixture of grouping terms or distributing here, so doing this mostly for space. That's our first one. The second one's going to be from 0 to 4. And this time we have the top again is 12 minus x squared. But the bottom this time is negative x. I got dx here. Alright, so the area. What's the total area of those things? Well, let's calculate it. So we're going to calculate the first one now that we finally got here. And we got our boundaries. We got around that obstacle. So I go to my graph, and we're going to calculate this from negative 6 to 0. I have a problem, I believe. I got to be including, yep, here it is. So I got to include my entire window. So I got to go from negative 6 to 4. So now when I go to my graph, that looks better. So I have to include this left boundary, otherwise it gives me an error. So if you had an error, make sure that you're including the boundary within your window. So we got to follow that calculation there. Second, calculate, number 7. We start out at -6, we work our way up to 0, and we get 72. Is it? That's a nice round number. 72 plus, let's find the other one. Now I'm going to switch around, which means I'm going to turn off this red minus blue, and we're going to go to red minus green. And this time we're going to go from 0 to 4. So I'm going to do second, calculate from 0 to 4 is the area. Whoops, did I do that? I did do that. Second, calculate the area from 0 to 4. And that's 34 and 2/3. 34 and 2/3. Put that all together and you get 106 and 2/3. Check, done. All right. So that was cool. That worked out pretty well. Now for this next one, it's more of an application problem. I'm actually going to be going over this in class, but the general idea is you choose 3 points. I really suggest you choose one on this y-axis, one on this x-axis, and then something else over here. And really what we're going to do is you figure out what's the area between these 3 curves, and it's a lot like what we just did, except the functions are a little bit easier. If you notice that here we have a top 1 and here we have a top 2, but we always have a bottom. So we're going to have an integral split here in the middle, and that's going to be, so it's going to be the integral from -2 to 0 plus the integral from 0 to, looks like I went to 4, and we got to figure out that first line, t1 minus b, and then we got to change it to t2 minus b. And how do I figure out lines like that? You guys got to consider that every linear equation is just y equals mx plus b, or you could do it by the point slope form, which is y minus y1 equals m times x minus x1, which simplifies further to m times x minus x1 plus y1. So it's going to be one of these two kind of formats that you type into your calculator for each of those equations. You set them up. I want you guys to try this one, see if you can figure it out. Actually, you know what? Screw that. Let's just do it. Let's just do it. We already got it far enough here. So I'm going to call this T1 blue line, and T2 green, and the bottom we'll call the red. So we got blue and green. What are these lines? Well, let's see. The blue, that's pretty straightforward. It looks like our slope here is going 2 to the right and 10 up. Oh, so that was pretty easy there. So that'd be y equals 10x, and then our y-intercept is plus 5. So there's, let's call that our y1. And then we'll have our green, we'll call that our y2. That's going to be a plus 5 there. We just got to figure out our slope. Whoops, not plus plus. What would our slope be? Well, we go down 5, so that's a negative slope for sure. And then we're going across here 4, so this is negative 5 over 4x plus 5. So we got negative 5 over 4x plus 5. And then the third one, this is probably the most complex because I'm not sure what the y-intercept is right there. But I could use this point here. That's the point -2, -5. And then our slope, looks like we have a run of 6 and a rise of 5, so that's going to be a 6 over 5 slope. So 6 over 5x for our slope. We don't really need the x in there if we're talking about slope. The slope is 6 over 5. So y3 equals, I'm going to be using this format here, the slope 6 over 5 times x minus the x value that I put in here, which is -2, So that's going to become x plus 2. And then plus the y value, which is negative 5. So just simplifying here, that's going to be a plus. Let's type those in. Let's calculate them. You know, simple, easy, super fast. So y1, what did I choose as my y1? That's 10x plus 5. And for the y2, that would be negative 5 divided by 4 times x plus 5. Then for the third one, we got 6 divided by 5 times x. You know what, let's put a times in there just so it doesn't get too confusing. Times x, oh, nope, we need parentheses, times x plus 2. And then it finishes off with some minus, I think, yeah, minus 5, plus a negative 5. So the first one is going to be blue minus red, so that's y1 minus y3. Vars, y vars. I know I already have it in the last one, but I'm just trying to keep things kind of clean here. And then the second one is going to be the green minus the red, so that's y2 minus y3. So vars, y vars, function y2. Okay, so those are two calculations of area that we're going to find. Let's graph them. Hey, look, that looks like our 3 lines. Perfect. There's a first area, there's our second area. So we got to turn off those original lines here. So turn off y1, turn off y2, turn off y3. And I'm going to turn off the fifth one because I don't need it yet. I'm just going to calculate the first one from, let's see, what would that be? From 0 to, not from 0, from negative 2 to 0. So we're going to go to graph. Second, calculate the area from negative 2 to 0. What do we get? That is negative 2.4. Is that right? For some reason that doesn't seem quite right. We got the blue, which was 10x plus 5 minus the red, which was our y3. Well, no, that can't be right. But let's see what's going on with our y equals. We got 10x plus 5. And then for y3, we got 6 divided by 5 times x plus 2 minus 5. Well, that's kind of crazy. You know what, I have, no, that wouldn't really change much. It shouldn't change there. So we got the blue minus the red, which is y1 minus y3. And we're going from negative 2 to 0. But now if I go to my y equals, if I go to my graph, this should be at 0 right there. That should be all the way up there. So something's off for sure in these functions. What is it? So this y1 here is negative 5. We'll move it to the other side. We got the y, negative 5. Okay, I'm going to go ahead and pause the video here, see if I can figure something out. And then I will come back to you guys. So I figured it out. I fixed the equation, and you guys are probably telling me from the beginning what was wrong. Sorry for making this mistake. But if you notice here, I have a 10 over 2 slope. Let's do that in blue so we don't mix our things. So that's not really 10x over 5. It's 10 over 2x, which is really 5x plus 5. So I fixed that first equation. It balances out the numbers this time. So now let's calculate this area. Second, calculate area from negative 2 to 0. And we get 7.6. So the first area is 7.6, or 7 6/10, or 7 3/5. Okay, so now let's get to calculating the next area. So now we're going to turn off the blue minus red, and we're going to turn on the green minus red. So I go to my graph, and that looks great from 0 to 4 there. That's a positive area. That's exactly what we want. Second, calculate the area from 0 to 4, and we get 10.8. So that's 10.8. Put those two together, what do you get? 17, 18.4. Awesome. Awesome, awesome, awesome. Now that's it. That's all we got. You know, some great stuff here. Remember that you need to know what your top, you need to know what your bottom is, you need to know what your left, you need to know what your right is. So if you answer these 4 questions for every integration that you set up, you will always get the area between curves. And in reality, you've been doing this all along. You just had to realize that when you have the area under a curve like this, let's call this y6. Why? Because we've just used a bunch of other y's. And let's call this y7, this bottom line. What does y7 equal? Well, it equals 0. And what's y6 minus y7? It's just minus 0, which equals y6. So this integral is what you've been doing all along. It's just your bottom line was 0, but when that line is not 0, you got to account for subtracting it from the top line. All right, that's it. Have a good day. Hope you enjoy the video, and we will see you in class.